Good morning all. I'll be presenting our ICCV 2023 paper Self-supervised Monocular Underwater Depth Recovery, Image Restoration and a Real-C Video Dataset. So as the title indicates, it's a self-supervised deep learning method which gives depth as well as restored image from a single underwater image, and we are proposing a Real-C Video Dataset also. Myself Nisha Varghese, I am from IPCV lab from Indian Institute of Technology, Madras. So the objective is to get a depth map and the restored image simultaneously from the input underwater image, and this is one example of our output. So we have depth map and the restored image from a single underwater image. So this, and both outputs obtained simultaneously in real time from this underwater image. This is an example input image from our proposed dataset Dhruva. And the motivation for this work is existing underwater depth estimation methods either use cues from haze or geometry, not both. There is no deep learning based network which simultaneously output both depth and restored image, and no real pair data for supervised networks, and no underwater video data sets which for utilizing geometry. So to face all these four issues, we have proposed our network UseReadyNet, which utilizes cues from both haze and geometry for underwater depth estimation, and which simultaneously output both depth and restored image, and it is fully self-supervised, and we captured and proposed a real underwater video dataset known as Dhruva. So coming to the state of the art, for underwater depth recovery or image recovery, we have it can be classified as two: traditional prior based methods and deep learning based methods. Traditional prior based methods has prior mismatch issues which causes incorrect parameter estimation. For deep learning based methods, can be classified as zero shot methods, supervised or unsupervised, or self supervised methods. Zero shot methods are time consuming since one image will be used for training and testing, and for supervised networks it needs paired data, but for underwater case there is no real paired data available. Here you can see some synthetic underwater images with the depth ground truth, but these are not real. For underwater image restoration also there are paired data, but they are not real. So the best choice is to use unsupervised or self-supervised methods. So our approach is fully self-supervised. This is the block diagram of our approach. Here I1 is the input underwater image. This can be disentangled into its components. So what are the components of the input underwater image? So we have used revised underwater image formation model in our algorithm. So I is the input underwater image. This can be given as J is a clean image, J into TD plus 1 minus TB into A, where TD and TB are transmission maps corresponding to direct signal and backscatter, and A is the global background light. So this transmission maps is related to depth using this relation TD is equal to e raised to minus beta d, where beta is the excitation coefficients. So from input underwater image it can be split to A1, J1, TD and TB, and these can be combined to get I1 reconstruction. So here we can compare I1 reconstruction and I1. This can be used for our first cell supervision. So and depth will be found out analytically from the transmission map. And we have another neighboring frame I2. From that also we will find the clean image J2, and between J1 and J2 there will be one pose. That pose will estimate using this pose net, and the depth and pose will be used to warp J2 to get J1 dash, and this J1 dash will be compared with J1. So this can be used for another cell supervision. Similarly, we are warping I2, the next image, to get I1 dash, and this I1 dash and I1 will be I1 should be ideally same. So this can be used for another cell supervision. So this is our approach. So in our approach, a clean image will aid the depth estimation, and a good depth will aid our clean image. So both outputs will aid each other. So these are the losses of our training. So for reconstruction loss we can use, because every components will be combined to get I1 reconstruction. So I1 reconstruction and I1 can be combined. So this is our cell supervision 1 using Hayes model, and this is view synthesis loss. Here J2 will be warped to get J1 dash, and J1 dash and J1 will be compared. Similarly I1 dash and I1 will be compared. So this can be used for the next cell supervision that uses geometry Q, and along with that we have used depth smoothness loss to avoid the discontinuity of depth in flat regions, and we have introduced channel wise depth consistency loss also to derive a single depth from all the transmission map. So we have two transmission map each with 3 channels. So for testing we have input underwater image I1, and we have found out clean image using SRNet, and transmission map using TMNet, and using transmission map and beta we have found the depth analytically. So we have obtained these two outputs simultaneously from the input underwater image. So this is one sample output from our network. This is a restored image, this is a depth map. This is another output, this is a input underwater image, restored image and the depth map. And our proposed dataset provides a first ever underwater video dataset, and it contains video sequences 20 artifacts, and each artifacts will have 360-degree azimuthal view. So this is an example of our one of the artifacts in our dataset. So it has 360-degree azimuthal view. So diver covers all the 360-degree views, and this is the camera path shown in this line. And this dataset can be used in underwater 3D reconstruction, NERF, video interpolation, extrapolation, etc. And 6 dataset we have used for comparison, and these are the networks used for comparison, and these are the depth outputs and restored output. Here you can see we have best depth results and restored outputs, and these are the quantitative comparison. This is already there in the paper, you can refer that. And these are some extra depth and restored outputs of underwater images collected from internet. So the conclusions: our method is fully self-supervised. We utilize cues from both haze and geometry, and we returns both depth and restored image simultaneously, and we have the best results, and we are computationally most efficient. In 18 milliseconds we have the outputs. Then our proposed dataset can be greatly leveraged by the research community. Thank you.